All right. So based on this research question, it is important to also tease out a hypothesis. And the hypothesis may be one tail or two tail. So when do we use a one tail hypothesis and when do we use a two tail hypothesis? In other words, what is a one tail hypothesis and what is a two tail hypothesis? A one tail hypothesis can also be characterized as a directional hypothesis in the sense that it stipulates the direction of the supposed relationship between the variables that are going to be correlated. And when I say it indicates the direction, it suggests whether the expected relationship is going to be positive or it is going to be negative. So an example based on these data sets, when we are using a directional hypothesis or a one-tail hypothesis, is that we can say there is a significant positive relationship between training hours per year and employee performance scores. There is a significant positive relationship between training hours per year and employee performance scores. Now, this is a one tail and it is directional because I have impugned in my hypothesis the expectation that at the end of the day, we expect that whenever training hours of employees is going up, then their level of performance will also improve. That will be a directional or a one-tail hypothesis. So when do we use a one-tail hypothesis? We normally use it when we have a theoretical justification or empirical evidence to tease out the direction of the relationship we are expecting. So maybe Hesberg's two-factor theory has already contended that the more organizations are able to provide adequate support systems, such as training opportunities for employees, it is able to also improve their contribution to organizational success. If this is the theoretical argument of Hesberg's two-factor theory, then we can, based on that, to formulate a directional or a one-tail hypothesis. Conversely, in some social circumstances, you may be new to the terrain where you are doing your investigation and you are not really sure whether the relationship you are expecting is going to be positive or is going to be negative. So under such circumstance, then you leave it at two-tail so that the final outcome will help you to do your conclusion. So two-tail hypothesis or a non-directional hypothesis simply suggests that you do not include in your estimation whether the expected relationship is going to be positive or negative. If you tease out your hypothesis in that regard, then you are dealing with a non-directional or a two-tail hypothesis. So if we were to be using a two-tail hypothesis, then this is how it will be. The relationship, there is going to be a significant relationship between training hours per year and performance scores of employees. If you say there is going to be a significant relationship between training hours per year and performance scores, then that will be a non-directional. So this kind of hypothesis will now be concluded after you've done with your analysis. Is there a question so far before I proceed to the test of the other assumptions, having set the research question and the hypothesis we are going to use for the investigation in context? All
Yes,
right.
please, can you,
Yes, hello.
please, can you go over with the two-tail hypothesis again for me, please?
Please get closer to your microphone. I'm struggling to hear you.
Please, I'm asking if you can go over with the two-tail hypothesis again.
Okay, the two-tail. So when you say you are using a two-tail hypothesis, it simply means that the hypothesis you are conjecturing does not indicate whether the supposed relationship will be positive or negative. It just gives a blanket statement that there is going to be a relationship between the variables. So anytime you state a hypothesis in that regard without indicating the direction of the supposed relationship, then you are dealing with a two-tailed hypothesis. And in using two-tailed hypothesis, we are able to determine the actual direction of the supposed relationship after we have conducted the analysis. And this is normally employed when you do not have enough literature or theory to support the relationship that you are trying to investigate. Please, is it clear?
Yes, sir. Thank you.
All right. And all these things that I'm talking about, there are options in the analytical tools for you to click. So depending on the specific hypothesis you have in your project work or the research question that you have, if it specifies that the expected relationship is going to be positive or negative, then you will have to take what? A one tail. But if it does not spell all these things out, but you want the outcome of the results to dictate where you will be centering, then you take two tail. Okay, so we already know how to conduct normality tests. For correlation, you will go to analyze. And please, are you still able to see my screen?
Yes, sir.
You will go to analyze, then you select correlation, a drop-down menu will come. You select bivariate. And by bivariate, the presumption is that we are going to check the relationship between only two continuous variables. However, there can also be a situation where you are checking the relationship between more than two variables. That one will not be correlation. That is what we call a point by serial correlation. For now, let's center on the bivariates so that once you're able to get the foundation, then we can be thinking about this point by serial correlation. So I said we are going to check the relationship between what and what. Who can recall?
So, sir, the training hours per year and performance score.
And the performance score. So you will select them nicely and move them into the variable box. And please, are you able to see my screen, how I'm toggling between the two tail and the one tail?
Yes, sir.
Assuming we are testing the hypothesis that there is a significant relationship between training hours per year and performance of employees, then we will have to select two tail. But if we are setting forth to check whether there is a significant positive relationship between training hours per year and performance scores, then we will have to select one tail. This is so because we are clear in our mind the part of the Cartesian plane where we expect this relationship to cluster. So under such circumstances, we use the one tail, right?
Okay. Hello, sir.
Yes, Nina.
Yes, please kindly come again. You said the relationship between the training hours and the performance score, we choose the two tail and then the one tail. Kindly repeat that side for me. Thank you.
Okay. Can someone just paraphrase all that I've been saying so far for Nina to grasp? Because it is just the things that I explained that I'm now practically demonstrating here. So I want one of you that was following keenly to recap what I said as far as this two tail and one tail is concerned for all of us. Who would like to try? Hello, are you all there? Hello?
Hello, sir.
Yes, I'm talking to the whole class. Someone should please explain when do we use the two tail, when do we use the one tail here? Because I have explained it. Ewua asked for me to even recap the two tail one, and I did explain it again, and it is coming back, which suggests that either all of you, your attention is not here, or something else.
Hello, sir.
Yes,
Doc, let
okay.
me try if I will be able to.
Okay, go on.
So at the beginning of our study, we are making propositions. We are trying to say that something will happen at the end of our analysis.
Okay.
That is, training hours is going to impact performance score. Doc is saying that if we are looking at the one tail, that means we are saying backed by a theory or an empirical study that at the end of the study, training hours is going to impact performance score because other people have said that before. So that's just one tail, and maybe the impact is going to be significant. So we propose that training hours is going to significantly and maybe positively impact performance score. That's just one. So at the end of the study, we are going to test if it was true or it is false. But then the two tails has alternate hypothesis and then a null hypothesis. That is where you give two phases. One, you say training hours is going to impact performance score. Then the other side, you say training hours is not going to impact performance score. You can bring the significantly and the insignificant. So that's about the one tail. One tail is giving one direction that at the end of the study, training hours is going to significantly impact performance score. Then the two tail is that you say on one side, training hours is going to impact performance score, but the
Okay.
hours.
Hello, Oche, we are losing you.
Impact performance score. So based on our study, we are taking. Oh, really?
But at least it's a good attempt. It's a good attempt.
Oh, I was thinking, I didn't know it.
It's okay. It's okay. Thank you very much for your inputs. What I would like to add is that at the stage where we are conducting correlation, we cannot be impugning impacts or effects in the relationship that we are expecting. So that is the part of the explanation that I do not want. Rather, we should be centering on relationship.
Okay.
All right. So when we say we are using a one-tailed test to conduct our analysis, it implies that we expect the relationship to either be positive from the outset or negative from the outset. And this is driven or anchored by some theories that we have at our disposal or by some literature that we have at our disposal. So if literature is saying that whenever employees are provided training interventions in our organization, it improves their performance, then in our hypothesis formulation, we can anticipate that indeed training hours will have a significant positive relationship with performance. So once we insert the direction, whether positive or negative, in the hypothesis, then we are using a one-tail test of significance. In some circumstances, we may not be certain whether the expected relationship is going to be positive or negative, and we want to leave it to the analysis to determine. For that reason, we will be checking both the negative side of the normal distribution and the positive side to see where indeed the relationship is going to meet and the direction it is also going to take. If that is what we are doing, then we are going to select a two-tailed hypothesis. Sorry, two-tailed significance test of hypothesis. So that is it. And depending on how you have stated in your project work. So if you, in your project work, you have stated that there is a significant positive relationship between training hours and performance scores, then when you get here, you are expected to select one tail like this. But if you have just stated that there is a significant relationship between training hours per year and performance scores, without indicating whether it is going to be positive or negative, then you select two-tailed box over here. And that will be necessary, that will be relevant when the output comes for interpretation. Another thing that you are also expected to take, depending on the version of SPSS you are using. So those of you that are using the one I said, you will have the option to be flagging significant correlations, which will be easier for you to discern whether the relationship you are observing is significant or not. So you can take this box, and apart from that, let me see the options. Okay, these ones, don't make any changes there. For the style too, don't make any changes there. So once you take all these things, then you click on OK. Just a minute. Are you able to see my screen?
Yes, Doc.
So can you see the
Yes,
output?
We can't see the output.
Okay. Can you see it now?
Yes,
Yes,
Doc.
sir.
Yes, sir.
Good. So this is a cross tabulation showcasing the relationship between training hours per year and, first of all, training hours per year itself, and thereafter performance scores also. Now, the same thing has been replicated down here, except to say that this time around, it is performance scores that is being correlated with training hours per year and the performance course itself. Now, in statistics, anytime a variable is correlated with itself, the correlation coefficient is 1 because it is the same thing you are comparing. And that is why the relationship between training hours per year and training hours per year over here is 1. But the moment you compare a variable with another variable, then you begin to get a correlation coefficient which showcase their the strength of their relationship. And by the way, there are thresholds for interpreting correlation coefficient, which I'll come to very soon. So normally, the correlation output is presented this way with all these, with the variables cross-referencing each other. And so the first one is where you are observing the correlation coefficients. And are you able to see the 2 stars here? There's 2 stars attached to the correlation coefficient.
Yes, sir.
Yes,
Anytime
sir.
you see a 1 star, a 2 star, a 3 star, sometimes you can get a 4 star when the precision is very, very high. Those stars indicate that the it indicates the statistical significance. And if it is 1 star, it means that the level of significance is being compared to 0.05 or 0.05. If it is 2 star, then it is being compared to 0.01. If it is 3 star, then the level of significance is being compared to 0.001. So,
Sir,
yes, hello.
please, can you go over again? You are going a bit fast, and some of us
Oh,
are taking
sorry.
notes. So thank you.
Okay. I'm saying that if you take a sober look at the first line, which indicates the correlation coefficient, it is normally accompanied by a star if the relationship is statistically significant. So anytime you see a star accompanying the correlation coefficient, the implication is that the relationship is statistically significant. The number of stars attached to the correlation coefficient indicates the level of significance that we are dealing with. Whether we are comparing it with 0.05, 0.01, 0.001, or 0.0001. If the star attached to the correlation coefficient is just 1, then it means that the variables correlate and they are statistically significant at 0.05 level of significance. So 1 star means the statistical significance is at 0.05. If it is 2 star, then the level of significance is at 0.01. 0.01. If it is 3 star, if the star attached to the correlation coefficient is 3, then the significance level is 0.001. 0.001. Fortunately, the moment you tick the box where you want to see whether correlation is significant, it will always provide a description beneath the box like this for you. So in exams, I can bring this box and then take out the description down here and ask you, what level of significance are we comparing this particular one to? Then you should be able to look at the star and tell us that because this one is 2 star, then we are comparing it with 0.01. Please, is it clear?
Yes, sir.
For the project work that you will be doing, normally, if you want to have consistent significant level that you are going to compare your thresholds to, you can always limit it to what is accepted in social sciences, which is 0.05. That will be acceptable. So under that circumstance, you'll be comparing this figure here with 0.05, and that should be okay. So the second column here also showcases the significance level. Then the third column indicates the number of participants or the number of cases that you have in your study. Then the same thing is replicated, just that this time around, it is performance score that is correlated with training hours first, then the correlation coefficient is received here, accompanied by the 2-star, followed by the correlation of performance scores with itself. And I'm saying that anytime a variable is correlated with each other, the correlation coefficient is always 1. The highest correlation coefficient you can get, which is perfect, is 1. And anytime a particular correlation coefficient is closer to 1, then we see the relationship that we are observing is very strong. So Cohen has a way of helping data analysts to interpret correlation coefficients. According to Cohen, anytime a correlation coefficient obtained is between 0.4 and 0.59, 0.4 and 0.59 can be characterized as moderate relationship, which means the relationship between the variables is moderate. Now, anytime you get a correlation coefficient below below 0.39, then that coefficient is weak. Any correlation coefficient below 0.39 is weak. Moreover, any correlation coefficient, according to Cohen, which is above 0.60, it is characterized as strong. In fact, the moment you are getting 0.8, then it is perceived to be very strong. So on that basis, the correlation coefficient we have here, which is 0.634, can be described as a strong relationship. So when we are interpreting this particular correlation coefficient, we can say that there is, and again, the sign that is attached to the correlation coefficient is positive. If it were to be negative, we will see a negative sign here. Okay, if it were to be negative, we would have seen the negative sign here. So because we are not seeing any sign attached to it, then it becomes positive. So we can interpret this output by saying that there is a significant positive relationship between training hours per year and the performance scores of employees. And this, the correlation coefficient of 0.034 is significant at 0. So you can use 0.05 if you are using the social science threshold, or you can report it at 0.01. In fact, this one is actually indicating 0.001. If you want to see the exact one, let me see something. Okay, this one is not showing the figures that way. Are you able to see the supposed figure that is being run up? The exact figure. Hello?
Hello, sir.
Are you able to see when I double clicked it? Can you see that another number is popping up, which is 3.0111 e to the power minus 18? So you can see that.
Yes, sir. Yes, sir.
When you convert this to a normal number, it means you are going to move to the left side 18 times, which means
Hello, sir.
Yes, hello.
Hello, sir. Please, mine didn't show. Is anything wrong?
Okay, so for yours to show, you will have to double click it. If you
did.
double click.
Yes, please.
Now
It's showing
use yes, so use your cursor to point the the 0.01, 0.001. Use it to point it.
Okay.
It will pop up.
It has shown in another table. It has come.
Exactly. Which version are you using?
Hey. I don't know.
I think you are using an earlier version. That's why.
Okay. So it says
Yeah.
27. IBM SPSS statistics 27.
27. Yeah, then you should be getting the same thing I'm getting here. I'm not sure where you are actually looking.
It has come, but the table popped up again and then it came.
Oh, okay. Okay, that's fine.
It has come. Thank you.
Okay. So that is correlation analysis. Any questions so far? Any questions?
Hello, sir.
Yes, hello.
Okay, so please, I wanted you to mention the one that you said is
I'm getting feedback from your end. So if you are having multiple gadgets there, just mute one of them. And then you ask the question. Hello?
Hello.
Go on.
Okay, so please, I was asking for the Cohen.
The Cohen.
One
Okay,
that's
okay.
moderate.
Yes, so Cohen is saying that anytime you get a correlation coefficient, which is ranging between 0.40 and 0.59, then it is characterized as moderate relationship. But if you get a correlation coefficient which is less than 0.39, then it is a weak relationship. The relationship is there, except that it is weak, which cannot be dramatized when we are making policy recommendations. Normally, when you are going to make recommendations for people to take you serious, you should go in with moderate to strong. In fact, if it is strong, then it is exceptionally good. However, if you're able to get something which is moderate, that is also substantial. And what does it mean when we say the relationship is strong? Strong will mean that you are getting something greater than 0.60. So anything above 0.60 suggests that the relationship is strong, according to Cohen.
Okay.
All right.
All right, thank you. Okay.
You're welcome. If there are no other questions, then I was supposed to demonstrate how to do checks for homoscedasticity, linearity, independence of the errors, having no outliers. But the same thing will be done in regression. So I will wrap this one up, then we will transition to simple linear regression, so that I'll take my time for us to go through all those assumption tests, which implies that even when you are doing correlation, in order for you to test assumption for instance, homoscedasticity, independence of observations, linearity, you will have to do it from the regression portion of the analytical tool. All right, unless there are further questions on correlation, it means we are done with correlational analysis, and then we will proceed to simple linear regression. Simple linear regression.
Sir,
Yes, hello.
please, so the correlation, is it for just like two variables? Or we can try it for multiple variables?
Yes, we can try for multiple variables. Very good question. So let's demonstrate that. If you do correlation for multiple variables, that is what we call point by serial correlation. Point by serial correlation. So are you still able to see my screen?
Yes, sir.
All right.
Yes, sir.
So for us to do check the relationship between more than two variables, you will go to correlation, select the bivariate But this time round, you will select multiple variables into it. Already we have training hours per year and then the performance course also in it. But we can also add other variables such as job satisfaction, employee engagement, and turnover intention. Then you bring them here. Once you do it this way, technically we call it point by serial correlation, because what is going to happen is that there is going to be the creation of a matrix that will compare all these variables with each other simultaneously. It is going to compare all these variables with each other simultaneously. In order not to make it confusing, let's just use 3 variables for now. And I'll later on come back and add more. So we are now checking the relationship across training hours, performance scores, and job satisfaction. All right, so all the boxes we've checked remain same. Then you click on OK. Then this is the output you will get. Can you still see the output box?
Yes, sir.
Very good. So now we have a matrix showcasing the relationship between training hours and training hours itself, which is 1, training hours and then performance scores, which is what we did earlier on, and now training hours and job satisfaction. Although all of them are statistically significant, the relationship between training hours per year and performance scores is more than 0.60. So we can interpret it as what? Moderate. No, sorry, it's more than 0.60. So we can interpret it as strong. But the correlation coefficient between training hours per year and job satisfaction is less than 0.40. In fact, it is close to 0.40, but it's less than 0.40. For that reason, it will be characterized as weak relationship. So unlike the relationship between training hours per year and performance scores, which is strong, the relationship between training hours per year and job satisfaction is weak. And at the same time, the relationship across these 2 variables and training hours per year are all statistically significant at 0.001. If you were to be reporting this in your project work, you just have to copy this and paste it in your Microsoft Word documents, and you do your interpretation. That should be fine. Is it clear?
Hello, sir.
Yes, hello.
You said with the earlier one, we used the 1 tail, but for this one that we selected, we went by the 2 tail.
No, the earlier one, I still use the 1 tail.
And this one is a 2 tailed.
No, sorry, the earlier one I used 2 tails. So you look at it here. Are you able to see it?
Yes, sir.
Yeah. If we want to do the 1 tail, we can equally do it. What will happen is that it will shrink. So the 1 tail is more stronger. When you are doing publications and when you are doing project work, we recommend you to be using 1 tail, because the expectation is that you've already done thorough review of theories. You've also done review of literature. So you should know where the direction that your hypothesis should be taken. So let's select the 1 tail and then boom. You see, there isn't much difference in terms of the statistical ways, because the estimation technique is the same. Can you see it?
Yes, sir.
Okay. Now, the last thing I'll be showcasing here before we proceed to regression is What about if we check the normality and all the assumptions and we realize that most of the normality index are suggesting the data is not normal? So what do we do? Under such circumstance, you will have to select Spearman instead of Pearson. Please, can you see what I'm doing here?
Yes, sir.
If your histogram, your QQ plot, your skewness, kurtosis, Kolmogorov-Smirnov, Shapiro-Wilk are all indicating that indeed the data is homogeneous, not normal. And again, your level of measurement too was not continuous. Then you are expected to use the non-parametric version of Pearson correlation, which is Spearman rank correlation. You select it like this, and then you click on OK. Yes, hello. I thought someone said hello. All right.
So
Yes.
once you select the Spearman, do you still make changes at the options or styles, or you just leave it like that?
Just a minute. When you say options, do you mean the one tail, two tail?
No. See, when you open the
Yeah, the stars. No, as for the stars, you mean flagging the correlation significance.
no, the options beside the variables table.
You mean this one?
Yes.
No, you leave it because these ones are normally going to generate the descriptive statistics for you. And before you get it, you must have already conducted those ones. So it will be redundant data that is going to make your output, it wouldn't make it economical. You will even struggle to know where to interpret from.
Okay. And sir, please have seen that you selected both the previous one. Do you select both Pearson and Spearman or just Spearman?
Only Pearson.
No,
But
for
I'm
the
saying
non-parametric
for the
option.
non-parametric, you will select only Spearman and you will untick the Pearson.
Okay, thank
Because
you.
Pearson is the parametric version for analyzing correlation analysis, and Spearman is the non-parametric version.
Say, can you do both at the same time?
Yeah, you can do both, but it wouldn't make sense for you to run both at the same time when you know your data is normal. If you know your data is normal, why will you be doing the Spearman and Pearson at the same time? That would suggest that you don't really know what you are doing. And if the assumption test suggests that your data is not fit for conducting Pearson analysis, then you go straight ahead to use the Spearman. It doesn't add up when you are doing the two. You are taking the box.
Thank you.
All right. And again, whenever you run an analysis, you are going to get a lot of things in your outputs. As much as possible, you have to be careful with the tables you select and report on. This is important because some of them may have no bearing or role to play in your study. So you don't present all those ones. Okay, later on when we start the regression, I'll be illustrating some of these things that I'm talking about so that it doesn't let you talk plenty just to try and interpret the output for testing your hypothesis or answering your research question. Now, regression. Okay, for regression, I indicated remind me to show you something. Whenever we are correlating or regressing, the basic tenet is that we are modeling. We are modeling. And whenever you model there is a way of representing them mathematically. In fact, that mathematical representation will also help you to do your interpretations. So let me share the, Can you see my screen?
Yes, sir.
So for regression, the mathematical model or how it is modeled is given by the formula on my screen. Y is equal to beta naught plus beta 1 x1 plus error term. Y is equal to beta, you can say beta 0, beta 1 x1 plus error term. The beta over here can also be replaced by alpha if you don't want to confuse the outcome that you are getting. So in some circumstances, others may change this beta and replace it with alpha. It is the same thing. Now, when you write the regression equation this way, what do they represent? The key variables or the alphabets in there, what do they stand for? The Y here stands for the outcome variable or the dependent variable that you are trying to predict, the dependent variable that you are trying to ascertain. So if for instance, you are doing an investigation on the impact of training hours on employee performance, then the outcome variable or the dependent variable becomes what? Performance of employees. Performance. Very good. The outcome variable becomes the performance of employees. The alpha or beta not here also denotes the constant, which suggests that when all things are held constant, what is the performance of the employee? So when we attenuate or when we reduce the efficacy of x1 and the error term here, what is the effect or the influence of the model on the outcome variable? That is the constant, right? Then the beta 1 here represents the correlation coefficient that we were seeing in the table. So let me go back to the table and for you to see what I mean by correlation coefficients. So you can see my screen now, right?
Yes, sir.
SAS 0.3, sorry, 0.634 na shahama. Any 0.380 na shahama. That is what we call correlation coefficients. And in the regression model, it is represented by beta. So beta 1, beta 2, depending on the number of predictors you have, you can have up to about beta 10. Okay. Now, the X in the model, where is it? So I'm saying the beta 1 here stands for the correlation coefficients. And the X1 here stands for the specific predictor or the specific independent variable that we are using to influence the dependent variable. So in our situation, the specific independent variable or predictor is what? The training hours per year. The training hours per year. Then we also have error term here. Error term simply refers to the amount of variance in the model, which is not due to our predictor, which that is the X here. So maybe we are thinking that in every organization, we can strongly predict employee performance by using number of training hours they have accumulated within the year. But in actual fact, performance of employee can also be influenced by the supervisory support that is available, co-worker support, salary. It can also be influenced, a number of factors. If all those factors are not captured in the model, then they are assumed in the error term. Please, is the explanation clear? So this is for a simple linear regression. A simple linear regression. For a multiple linear regression, what will happen is that you are going to have multiple predictors. So for multiple linear regression, you are going to have multiple predictors. In our example that we just witnessed, we were using training hours per year. We were also using employee engagement, job satisfaction, and all that. So if you are modeling and you have several independent variables in it, then it will not be relevant for you to be conducting simple linear regression, because simple linear regression is used when you have only one independent variable and one dependent variable. Anytime you have one dependent variable but multiple independent variables, then we employ what we call multiple regression. And that is given by the equation on our screen. So the beta k and the sk here denotes the last predictors that you may be using. So if the last independent variable is like 9, then the beta k here will be beta 9 x 9. If it is 20, it will be beta 20 x 20, then the error term. All right. So strictly speaking, these equations are what we call estimable equation. Estimable equation. They are called estimable because it projects the mathematical model that we are going to investigate. So estimable equation. The one above is what we call estimable equation. The moment we start inserting the correlation coefficients in it, then it's changing from estimable equation to what we call estimated equation. So the one above, where is it in Paul? This one. If you want to make it estimated equation, what is the, let's go back to the box and take note of the values over there. The outputs. Now, can you see my outputs on your screen?
Yes, sir.
So put in your mind, the coefficient is 0.634. Okay, so let's go back and insert it. 0.634, 0.634. So to make it estimate, we say the way, so y is what? Y is what? Hey, ceremony. The Y for the
There is
regression
the dependent variable.
and in
That is
the
outcome.
outcome
It's the
variable,
outcome
what is it?
variable that we are trying to ascertain.
Yes, and the outcome variable is what? The outcome variable of interest is what? Is performance.
Yeah.
It's performance. Is that not the case? Eh?
Yes,
Yes,
sir.
sir.
Yes, dog.
Performance. Then the beta naught plus beta 1. We said it is 0. What? 0.634. Anna.
Yes, please.
Into bracket. The independent variable is what? Training hours. Training hours. Then plus the error term. Error term, no cry. So me fan say error term like this. Plus the error term. Now, the moment you express the equation this way, we call it estimated equation. In fact, when we run the regression, let me do that so that we get the constant and everything, then it will be easier. So let me switch to where Can you see the screen?
Yes, dog.
Okay, for regression, you go to analyze regression like this, linear. I'll come back and explain a few things, but let me get the constant and way first. The dependent variable is what? Performance. So you select that one and put it here. And the independent variable is what? Training hours per year. Then you put that one here. I'll come back and explain certain things here. But I just want to generate something in line with the correlation so that you understand how to generate the estimable equation. Sorry, the estimated equation. Okay. So the estimated, you are going to use, you see in the model there is constant. Some model when y is equal to beta naught. No? The beta naught is your constant here, which is 71.3346. So 79.346. Just a minute. So 79.346.
71.
It's 71. Hey, Asemo.
Yes,
Thank
sir.
you. Let me confirm again. Yes, you are right. Thank you very much. 71.346. Okay. 71.346. And then the error term, the standard error is this one, 1.571. 1.571. So let me go and insert. Error is 1.571. Okay. The moment, let me switch back to the Microsoft Word document.
So please, the performance figure is still not corrected. It's 71.
It's 71. And so let me do it. Maybe 70. Like this, right?
Yes, please.
Yes, sir.
So 71.346 plus the coefficient into bracket training hours plus the error term. Okay. So the moment you run your regression and you put the various values into the equation like this, then you get what we call estimated regression equation. Estimated regression equation. These are the first things I want you to note as far as modeling in regression is concerned. The first equation, which is whether simple linear or multiple regression, is what we call the estimable regression equation. And this is the estimated regression equation. And some even characterize it as the final regression equation, because later on I can give you some specific values for us to predict that if, for instance, we are able to increase the training hours for the year to 300 hours. What is the likely outcome of performance we should expect? Then you put the 400 hours here and you do the multiplications. It will give you the expected performance outcome we should anticipate. Is the explanation clear so far before we proceed to how to actually run regression? As far as estimated and estimable equations are concerned.
Okay, so please, I have a question. I just want a little clarification on the X1. The X1 that was represented with the training hours.
Okay.
So does that mean in any question where we see the training hours, as you said, like maybe if it's 400 hours per week or year, then we multiply it because it's in the brackets.
Exactly. You will put that figure here.
And then we multiply it with the
correlation
7.1.
coefficients. No, you multiply with the coefficients, and whatever you get, you add it to the constant and also add the error term. Look at the equation well. It is the constant plus 0.643 into bracket training hours plus the error term, which is 1.57.
Yes. Okay. So I will just multiply the training hours with the 0.634 plus
and then
71.364, and then plus the
1.57. Yes, and that will give you the estimated performance for that particular number of hours you are interested in.
Okay, thank you.
Yes. And before we proceed, let me also add one thing. The correlation coefficient here, this one, it's for if you are trying to interpret it, it is interpreted by saying that a unit change in training hours results in a 0.364 changes or scores in performance. Let me take it again. If you want to interpret this correlation coefficient of 0.634 here, this is how we do it. We say that a unit change in training hours per year will result in, because it is positive here, it will result in an increase in performance score by 0.634. Should I repeat it again?
Yes, Doc.
So whenever you are interpreting the coefficients, correlation coefficients, you have to be guided by the sign before it, if it is positive or negative. In this particular instance, it is positive. So the implication is that a unit change in training hours, when it's a unit change, which means when it's changed by 1, it will result in a positive, it will result in an increment in performance score by 0.634. A unit change in training hours will result in an increment in performance score by 0.634. That is how you interpret the correlation coefficient over here. Assuming you were just looking at this table. Let me go back. Mhm. Assuming you are looking at only this table to do the interpretations, then that is how you do it. So let's proceed to the steps in running regression. Then we will take our time and look at it. So yes.
Before we go on, please can you go back to the equation? I got confused a bit.
Okay. Let me go to that slide. Can you see it now?
Yes, please. So I'm saying that the equation can be, the whole thing can be in a negative. So it will be y equals b, the constant minus
Yes. It can be y is equal to negative constant minus beta 1 x1 minus error 10. Because so that is why we call this one estimable. The estimable one will not indicate the directions of the supposed figures or values that you are going to get. It is only when you have finished estimating it that you will see in the output that indeed the direction of the correlation coefficient is negative. The direction of the error term is also negative. And for that matter, you will modify it and change the directions accordingly in your final equation. So it means that you have to be guided by the values you are getting from your regression results. Yeah, you can ask your question.
Maybe next week. Right now, I'm too confused. So maybe next week or you
as someone. Okay.
Hello, sir.
Did you be fine? Yes, hello.
Okay, so please, I wanted to find out if the estimable equation and then the estimated equation are the same.
No, they are not the same. The estimable one is more or less like a theoretical formula for how every regression is supposed to be modeled. But the estimated one is the equation that reflects the reality of the model you are handling.
Okay.
It reflects the reality because it will now showcase the exact direction of the correlation coefficient as well as the error term.
Okay.
So assuming in our estimation, we got the coefficient to be negative 0.634. You remember I was saying the correlation indicates the relationship, which can be positive or negative. The positive will show whether it is going the positive negative will show the direction it is going. So if you get negative sign attached to your correlation coefficient, then when you come to the estimated equation, you have to also put the negative sign there.
Yes, sir.
Yeah. Okay. So running regression. You will go to analyze. Are you able to see? No, let me go to that particular slide. Is it visible now?
Yes, sir.
Okay, to run a regression, you select analyze, regression, then linear regression. Linear regression. And if you are doing simple linear regression, then the expectation is that you are going to check the effect or the influence of an independent variable on a dependent variable. So under such circumstance, we can check the effect of training hours per year on performance score, like I have selected into There are various boxes here now. Then you come to statistics. For simple linear regression, check the model fits box, check the estimates box, and also check the descriptives box. Now you also check the Ben Watson. The Ben Watson. We use, you remember I indicated that for correlation and regression, it is important to check some specific assumptions. For independence of errors, which is an assumption to be checked in correlation and regression, this is what you will use to test that particular assumption. The Ben Watson. The Ben Watson. All right. Assuming we were doing multiple regression, then we would have checked for collinearity. But if you are doing simple linear regression, you are just having two variables. So there is no need to check collinearity. Again, assuming we were doing multiple regression, we would have also checked the R-squared changed, so that anytime we introduce an additional variable into the model, we will see the amount of variance in the dependent variable, which is employee performance, being explained by the additional variables that we are also introducing. But for now, simple linear regression, leave it unchecked. Now, so you click on continue. For plots, check Z predicts, and the Z scores for the prediction and the residuals. There is also another assumption we have to check. We have to test, which is on the normality of the residuals. To do that investigation, we use the Z scores of the predictor and the Z scores of the residual. So you select the Z scores of the predictor into the X. Because in our regression model, the predictor or the independent variable is represented by X. And the residual will now be the one we are coming to predict, which will be the Y. So you select all those things, then you check histogram, because it's the histogram that is going to create the normality test for the residual for us to see whether it falls within the Cartesian plane. Then you also check the normal probability plot. Okay, you click on continue. Then click on save. Now, for simple linear regression, there is no need to even save anything here. But if we were doing multiple regression, then we would have used the unstandardized. Okay, let's save the unstandardized scores. Then we are also interested in Cook's. So when do we use Cook's? We use Cook's test whenever we are trying to check whether there are outliers. Don't forget, one of the assumptions in correlation and regression is to check whether there are significant outliers in your data set. So the Cook's distance will help us estimate whether indeed there are outliers. So please note it down. We use Cook's distance to check for outliers in a data set, and we use the Ben Watson to check for the independence of the errors. Yes, for regression, these are the most important things you have to select. Then you click on continue. Options. Okay, for the options, leave it default. For the style to leave it default. For the style to, for the bootstrapping, that one to leave it default. Any questions so far before I proceed? If there are no questions, then you click on OK. Can you see my output box?
Yes, sir.
Very well. So normally when you are running simple linear regression, this is the output box that you are going to get. But because we are interested in testing for, so you get the one for the descriptives to see the mean scores. You get the correlation, which is just like what we did. Do you remember, do you recognize this figure from anywhere? The 0.634. Do you remember it from anywhere?
Yes, sir.
Where did you recognize it from?
So the correlation coefficients for the first one that we did.
Exactly. So that is why I inputted those coefficients in the estimated regression equation, because I knew correlation and regression is the same thing. The only difference is that when you get to the model summary table, then you start squaring the correlation coefficient to get your adjusted R square. So do you recognize this value 2 from somewhere? The 0.634. Do you recognize it from somewhere? This 0.634. Do you recognize it from somewhere? Or have you seen it elsewhere before? It is the same correlation coefficient here. The correlation coefficient for the relationship between the variables. That's the same thing that is presented as the R value. How do you interpret the R value? In fact, I'll come to the interpretation, but let's go through the various tables that you get. So it is this same correlation coefficient that is squared. If you have a calculator beside you, just square 0.634, you'll see that you get this figure. You get this figure. All right. Then this is the Debin-Watson score. This is also the ANOVA table telling you the significance of your model, whether the modeling that you are doing is statistically significant for us to take you serious. And that is where you use the F test and the sig value here to also check. It also gives you the coefficient table. And it is from this coefficient table that you are going to get your standardized and non-standardized coefficients. And when we are filling our estimated regression equation, it is the unstandardized beta coefficients here that we use. So we will have to go back and modify it and use 0.694 instead of 0.634, because we normally use unstandardized correlation coefficients. And this is the constant or the beta knots that I was talking about, and this is the error term. And this one too is statistically significant. Then the residual statistics. The residual statistics gives us two relevant information. One is the standard residual, the standard versus the student residual scores here, and the Cook's distance, which is also here. I'll later on come back for us to interpret it. Then the histogram that we were using to plot whether the residuals are also normal. And once the residuals are normal, then it means that that assumption has been satisfied as far as, how do you call it? That normality of the residuals is concerned. Then the, how do you call it? Yes, we also use the PP plots to check whether within the diagonal line the data points cluster around it. That is, they are not too far from the diagonal line. So you can also use the PP points to check the normality of the residuals. And you can also use scatter plots to check whether there are outliers. You can use scatter plots to check whether there are outliers. Normally, they fall within plus or minus 3. So there are some higher scores, except to say that they are not outside the plus or minus 3, which indicates that there are no outliers in the data. So as far as testing the assumption of outliers, you can use this scatter plot. In fact, some go extra length to even insert an imaginary line between the data points to indicate that indeed there are no outliers. So if you want to insert that imaginary line or line across it, all you need to do is to double click the charts. If you double click it, you are expected to get a window like this, which will activate you to make some additions and subtractions. Are you able to see the changes in the on my screen?
Yes, sir.
Yes, sir.
Good. And depending on the direction of the majority of the data points, this one, it is horizontal. So you select that horizontal line like this, and it will draw the imaginary line across them for you. Thereafter, you can close the chat box. Then the imaginary line will set in. Come on. On the eye deeper down here. All right. Now, how do you interpret? Let's start from the assumption. So, with respect to the check for whether there are significant outliers in your data sets, you can use the scatter plot to do that. And what you will be looking out for as far as the scatter plot is concerned is that you don't expect to get any data points outside the -3 here and the +3 here. And it can be observed that all the data points are scattered within the ±3 of our data points. So that is an indication that there are no outliers in our data points. Then there is also normality of the residuals. You remember I created the z-scores for the residuals and the z-scores for the predictor. That is what I've been used in drawing the histogram here and the PP plot here, which this one suggests that the residuals are normal, and this one also suggests that the linearity assumption has been achieved, because one of the assumptions preceding the conduct of regression, simple linear regression and multiple regression, is that the relationship that is assumed between the dependent variable and the independent variable should be linear. And if you take a sober look at how these data points are clustering around the line in the diagonal line, you realize they are all mimicking the direction and scattering around the line, indicating that linearity assumption has also been satisfied.
Doc, I wanted to ask on the scatter plot. What if you find there is an outlier?
Come again?
Yes. If you find an outlier which is not within the ±3, what do you do?
If there is an outlier, then that one, there are so many ways of remedying the situation. And each of them that you choose it should be based on, or you should justify your decision by an authority. So some of the authorities contend that if the outliers are few, then you can go back to the data sets and delete those specific cases from your data sets. Are you following? You can go back to the data sets and do away or delete those specific outliers that you are confronted with in your modeling. Other authorities also suggest that rather than deleting it, you can rather use the logarithm strategy, wherein you will now log the log of all the data points. And that one will give you a standardized version of the data points, which will now be okay to run for your analysis, which means you are not going to run the main data set that you have. You will have to create log of the data set and use the log of the data set to run your analysis. Others are also of the view that, yes, let me say the last one. Others are also of the view that instead of using the logarithm strategy or deleting the data points that are outside the realms of the scatter plot, you can use the next closest, you can approximate it to the next closest score. So assuming the next closest to the outlier, which is about 40, is 20, and 20 is falling within the norm, then you will now have to reduce them to the 20, which is their next closest. So every option you will select, you will have to anchor it with an authority that suggests that will be more, it will be feasible given the circumstances you are analyzing your data in. You can go on with your next question.
No, I'm okay. I said I was going to side with the deletion.
Okay. And it's not, if you want to make matters easier for you, then you go with the deletion. But sometimes too, maybe coming back from the field, you administered about 1,000 questionnaire, and after 3 months, only 80 has been filled. And I say, under normal circumstances, that cannot be justified for a project work at the master's level. But at the master's level, we expect you to be having higher sample size so that your estimations to the population can be cutting edge and precise. So if your data set one is then you will be constrained to go by the how do you call it? The logarithm approach, which is equally acceptable, or the other one. Okay. Which one was I even going to? This table, the residual statistics table. The residual statistics table will help us to test a number of things as far as the assumptions of the regression is concerned. First, it helps us to check whether, so there is, where is it in Pokra? The residual scores over here. The residual scores, the standardized residual scores and the student residual scores over here. That one can also be a basis of affirming whether you're kind of saying, if your scatter plot is not giving you an affirmative basis to interpret your data, then you can also use the standardized residual scores over here. The threshold is that we expect the standardized residuals to be within the range of plus or minus 3. Plus or minus 3. So anything below that suggests that the outliers that are in your data set are not so significant. It is manageable. And in this particular simulation we are doing, the standard residual scores are well below the plus or minus 3 that is the threshold. Then the Cook's distance. We normally use Cook's distance values to also affirm whether there are outliers. Cook's distance. So the minimum and the maximum over here is what we pay attention to. Anytime you get a value here, as far as Cook's distance is concerned, anytime you get a value that is less than 1, a value less than 1 indicates that there are no outliers. I'm not saying 0.01 or anytime you get a number which is less than 1, then it also suggests that there are no outliers. Then there is one more. That they've been Watson.
So Doc, I respectfully I want to find out what if maybe the scatter plot is saying there's an outlier, but then Cooks is saying there's no outlier.
No, it will never happen that way. So sometimes you will get a data point which is somewhere here. I don't say well, -3. You will be getting a data point which is somewhere here. And you are not so sure whether it is outside or inside. You may also get some data points which will be somewhere here. And you are not too clear whether those data points that are on the borderline are inside or outside. That is where you fall on the Cook's distance and the student and the residual minimum and maximum scores over here. Because those are the same data points that are plotted within here. Is it clear?
Yes, Doc.
Now that they've been Watson, I think I've mentioned it before. I don't know whether the time we came face to face and that's the last time we did online. But anyway, when do we use or when does the Debin-Watson component becomes necessary? We use the Debin-Watson portion of the model summary to test the assumption of independence of errors. Independence of errors. The residuals or the error term that we are experiencing in the model, is it really due to chance or it is because of the manipulations of the independent variable we are introducing as an intervention? It has thresholds that we use to do the interpretation. So by rule of thumb, anytime the value of the Debin-Watson here, this particular value, anytime it is closer to or near 2, please, are you following? Anytime it is closer to or near the value 2, not 0.2, 2, then it means that we have achieved an acceptable independence of errors in our data sets. But beyond this, if you get any value which is less than 1.5, then that is an indication that the Debin-Watson score is positive. It is positive, but not acceptable because it is far away from 2. Now, if you get a Debin-Watson score which is greater than 2.5, 2.5 is far away from 2. That one is also an indication that the Debin-Watson score is negative, and it is pointing towards the negative direction. And that one is also not acceptable. So we always want the Debin-Watson score to cluster to be closer or near the value 2 so that we can be convinced that the error term or the residual score that we are receiving is independent of any other extraneous variable that we might have not considered. Is it clear?
Yes, Doc. But how close? Maybe 1.6 to 2.4?
That is why I'm saying any value below 1.5 means it's not acceptable. And that would be indicating that is actually a positive derivation score, but it's not acceptable. But any value also greater than 2.5 is also far away from 2, and that is also not acceptable. In fact, there are indications of there are cause for alarm. All right. So that is how we test the assumptions for regression. Having done these things, how then do you interpret your regression? So normally we start from, for regression analysis, we are interested in the correlation coefficients over here. We are also interested in fact, for a typical regression analysis, this is a simple linear regression. We are interested in the R square over here. The R square over here. If your sample size is less than 50, then you are expected to use adjusted R square. But if your sample size is greater than 50, then the value of R square over here suffices. What is the R square? R square simply explains the amount of variance changes in the dependent variable, which is caused by the independent variable. The amount of variations, changes in the dependent variable, which is caused by the independent variable. And we normally multiply the R square value by 100. So if you multiply 0.402 by 100, you are going to get 40.2%, 40.2. So to interpret, we will say that the amount of variance in performance of employees explained by training hours per year is 40.2%, which is huge because there are so many other variables that we can use to predict employee performance. And in a simple linear regression, we are using only training hours. And training hours and to me explaining over 40% of the variance in performance cost. And that is huge. So that is how you can interpret the model summary table. You interpret it by saying, by looking at the R square value over here. And you multiply it by 100. And whatever you get, you will see that. So when you get that, it's a matter of semantics and your own way of summarizing the table. If I am writing it, I can say that 40.2% of the variance in performance score is explained by training hours per year, and that should suffice. Now, how significant is this 40.2%? To know that, we have to look at the ANOVA table. So for the ANOVA table, we are also having a sig value of 0.001. 0.001 is, if you multiply it by 100%, it is 1%, which is very, very significant. So this explanation power, which is 40.2% of the variance in employee performance provided by training hours, is statistically significant at 0.001 level of significance. Now with the F value, no, as a bracket. No. Now we want to know the effect size. The effect size of training on performance. So if you want to know the efficacy or the effect size, that is where we look at the coefficient figures. The coefficient figures here. The effect size, we normally use if you are reporting it on, if you are reporting it using APA will prefer that you use the standardized coefficients because that gives you the real value. And I'm kind of say the nominal value. It gives you the nominal value of training hours efficacy on employee performance. But the unstandardized one is what we use whenever we are reporting the estimated regression equation. And as I indicated earlier on, this is the constant. So the effect size of training on performance, going by Cohen's rule of thumbs, this one too will be the effect size will be strong because it's greater than 0.5. The effect size is greater than 0.5. And the last thing we will look at is the significance, the t-value and the significant values that are attached to it. Training is having a positive and statistically significant effect on employee performance. Because if you look at the t-value here, it is positive and the sig value is statistically significant. So you will say training has a significant and positive effect on performance scores of employees. And that should be enough for you to interpret all these outputs. Any questions so far as simple linear regression is concerned? If there are no questions, then we will quickly look at multiple regression. So when do we use multiple regression? Yes, hello.
Sir, please, I have something to say. Please, right now, I don't know how to put it. Please, respectfully, can we do the multiple next week? Right now, for me, it's like everything is jumbled up in my head. And I feel like
don't worry. You will get it's just like what we've done. You will get the recorded video, then you take your time to digest it. Because next week, we are supposed to tackle the assignment, the data set that I've given you, and we were going to lose a lot of things if we put some of them in the free. So that is why I'm recording everything for your later reference.
Okay.
All right. So for multiple regression, when do we use multiple linear regression? And by the way, they are all part of the general linear regression model. We normally use multiple regression when you have one dependent variable, but more than one independent variable or predictors. You have one dependent variable, but more than one independent variable or predictors. And under such circumstances, it is important for you to put all the variables into the model in order to avoid committing type 1 error. Because the moment you do repeated single linear regressions, then you are likely to say that each of them is statistically significant. But in fact, if you put all of them in your modeling equation, then you are able to see it properly. So for multiple linear regression, you go to analyze regression, then you come to linear. In our instance, the dependent variable is still performance score, but the independent variable, we are supposed to introduce additional variables into it. So which one should we add? Let's add job satisfaction. And let's say employee engagement. Okay, in fact, let's add turnover intention because there's no time. Good. So the argument we are advancing is that employee performance can be explained properly when we consider their training hours per year, their job satisfaction, their level of engagement, and their turnover intention, which regression is going to help us test this. For the statistics, you will now take the R-squared changes because anytime you introduce an additional variable, you are going to see changes in the R-squared. Then for the plots, it's the same thing. For options, that one too is the same. All right. Then click on OK. Good. So we now have a matrix showcasing the mean scores, as far as the descriptive is concerned, the mean scores for all the variables. So for the dependent variable, which is performance, we have 85.891, and the predictors, we have 20.959 for training hours, job satisfaction 3 point something, employee engagement 3.9, turnover intention 2.0061, indicating that before we even proceed, it means turnover intention is quite low in that organization. Of course, we will have to check whether that is statistically significant, but that of engagement and satisfaction are all above the average. All right, for the correlation, there is something that we have to check here. Because we are doing multiple regression, an additional assumption that you have to check is what we call multicollinearity. Multicollinearity. What is multicollinearity? Multicollinearity is said to occur anytime a particular variable, the relationship between two or more variables, is more than 0.70. Anytime the relationship between two or more variables is more than 0.70, if that is the case, then it means that definitely when you run the regression, you are going to expect positive relationship between them. So the rule of thumb is that when two variables are highly correlated, or we experience multi-correlation, then there is no need to include them in the regression modeling. So based on our screen over here, the relationship between employee engagement, job satisfaction and performance scores here is a little above 0.70, which means if this were to be a project work that we are undertaking, you will have to justify why you still want to include job satisfaction in the model, because right from the outset, the two variables are behaving, or they are behaving the same way, which is likely due to the fact that the data set that you collected, you have manipulated it. Copy we are not and when you bring it, it will expose you. Other than that, if you get anything below 0.70, then that should suffice. As far as test for multicollinearity is concerned. Then test for, so the next table is good. I would say previously, the R-square was explaining 0.402% of the variance in the model. So when we use only training hours, we were only explaining 0.40, which is like 40% of the variance. But by including turnover intention, employee engagement, and job satisfaction, the R-square has now increased to almost 67% of the variance in performance were being explained by the following predictors, which by interpretation is very strong. In fact, we analysis R square BC adjusted R square like this, then that means your model is very good. And what does your model being very good means? It means all the factors that are supposed to be considered in estimating your dependent variable have already been considered, which is a good sign. The Debin-Watson's is already around 2, which is okay. The ANOVA table is also significant, indicating that this approximately 67% of variance in performance explained by the predictors is very robust. Now, the coefficient tables. Look here. I want to say some of the coefficients are negative. Can you see it? Some of the coefficients are negative. Good. So that is what I meant, that when you are finally writing your estimated regression equation, you have to be guided by the direction of the coefficient. So for engagement, the sign will be what? Negative. For turnover intention, the sign will be negative. For job satisfaction, it will be positive. And for training, it will be positive. And note, another thing that I want to bring to your attention is when you are making recommendations to management. Although these figures here are showing us the directions and the impacts, are those impacts statistically significant? So look at the t values and the sig values. For training hours per year, it is statistically significant, which means when you are making recommendations to management as with respect to the interventions they can focus on to enhance the performance of employees, training hours has to be part of your recommendations. Again, job satisfaction has to be part of your recommendations because it is statistically significant over here. But you cannot recommend employee engagement. This is because it is not statistically significant. You cannot also recommend turnover intention to management because it is not statistically significant. So that is how you will look at it to make recommendations to your management. Other than that, the rest are just like the simple linear regression we did in the previous way. So unless there are questions or clarifications, I'll end the class here and we'll continue, God willing, next week. Are there any questions?